So in Chemical Kinetics 1, we determined the rate law of a crystal violet plus hydroxide solution by using the integrated rate laws and the method of initial rates to determine the exponents on each one of the reactants. This week, or in Chemical Kinetics 2, we're going to be looking at Arrhenius and the activation energy of that same reaction. So the rate constant is the part of the rate law that is temperature dependent, and we know that if we increase the temperature, we're going to increase the rate of a reaction. If we just look at the Arrhenius equation, it's not necessarily straightforward to understand that as the temperature increases, this exponent is going to decrease, but it's going to become a smaller negative value, and that's actually going to increase the rate constant. The activation energy here is also in that exponential term, and as the activation energy increases, then this whole term becomes a larger negative number, and the exponential of a larger negative number is going to decrease the rate constant. What the Arrhenius equation really tells you about is the activation energy, which is the amount of energy that's required, right, for to get the reaction going. And the denominator, RT, is really telling you about how much energy is available. So how much energy do I need and how much energy is available? And the ratio of those two things. So if I have some activation energy and I'm at low temperature, I don't have enough energy to overcome that barrier. But if I have a high temperature, then I have a lot of energy and I can overcome that barrier more easily. The Arrhenius equation describes that dependency of the rate constant on temperature, and it also provides a way to measure the activation energy of a reaction. So in order to do that, in order to measure the activation energy of the reaction, we can take the logarithm of both sides to kind of get rid of that exponential function, and then rearrange it a little bit so that we can clearly see the linear form of the line y equals mx plus b. So y would be the log of the rate constant on the y-axis. X on the x-axis would be 1 over t, or the inverse of the temperature in Kelvin. And then the slope of that straight line would give you the activation energy over r. So we could just multiply that slope by r and we'll get the activation energy. You'll also notice that the intercept of that line will be the logarithm of the frequency factor a. If we then plot the log of k versus 1 over t, we should get a straight line, and then we can determine what the slope or activation energy is, and we can determine what the intercept is. This is going to require us to measure the rate constant at multiple different temperatures. So our strategy for Kinetics 2 is that we know from Kinetics 1 the rate law, we know the exponents for hydroxide and crystal violet, and we know we can write a rate law, a condensed rate law with a pseudo rate constant, because the concentration of hydroxide is so much greater than the concentration of crystal violet that we can assume that it's relatively constant over the course of the reaction. So if we know the concentration of hydroxide and we know what y is from our week 1 experiments, we can measure the rate, right, as a function of crystal violet, and we know what x is, so we can measure the concentration of crystal violet over time. We can determine what k prime is from our integrated rate laws, and then if we know hydroxide and y, we can solve for the rate constant. So our goal is to measure k prime to find k as a function of temperature so that we can determine the activation energy and the frequency factor for this reaction.